This is Mark Staples. I'm the director of the Gallatin National Forest Avalanche Center, formerly the director of the Utah Avalanche Center. And after Bruce's great summary of all the sources of energy and how they contribute to heat going in and out of the snowpack, we're going to dive right in and explore 5 different weak layers and how they form. Of note, what we're going to do is talk about how they form. In many cases, they form all the time. And the key thing to remember is that in order for them to become a problem, they need to survive and then get buried. Whether or not they do, Bruce will touch on in his 3rd video when he talks about wind and precipitation. But for now, let's jump back a few years to January 2020. Imagine you're walking into the office as I was that year, and as Craig is doing here in Salt Lake City. It's a fairly typical winter snowfall. You think you have a good handle on things. Most avalanches were happening on slopes just like this, producing avalanches like this and like this one on these shady north-facing slopes. And as you sit down to write the forecast and look at weather models, at that time, I felt like I had a pretty good handle on things. Those avalanches had actually started to become fairly unlikely because the snow had gotten so deep. And as I'm looking at weather models, imagine you get a call, as I did, from the Utah Department of Transportation at 5 a.m. saying they had just triggered a huge avalanche about 1,000 feet wide in sunny south-facing terrain, just like this. And seemingly overnight, those avalanches on those shady slopes had become unlikely and almost ceased to be a problem. And then the situation had completely reversed itself to where avalanches were now very likely on these sunny slopes. So what happened? How did the situation get completely reversed seemingly overnight? Well, to answer this question and to go over some common weak layers, we're going to use this nice simple table that Bruce put together, summarizing the different types of weak layers and the processes that form them, the time frame in which they form, where they form in the snowpack, the primary forcing mechanisms, and the aspects where you can typically find them. So let's start with the classic one, depth hoar. It forms over a longer period at the bottom of the snowpack, mostly on shady aspects, produces avalanches just like this one, breaking right at the ground on that old faceted snow that typically forms early in the winter, late in the fall when you have thin snow. And as we all know, it's warm, right about 0 degrees Celsius at the ground. And then the snow is much, much colder. So you have a big temperature difference over a short distance that causes a large temperature gradient. So the question we want to answer is, when we think about the energy sources and heat, is why is the snow surface so cold? You may remember this depiction of all the different sources of energy. Now, one certainly that comes to mind that can make the snow surface cold is bitter cold air temperatures. It's not uncommon in December or some other part of the winter to have an Arctic air mass come in, bring very cold air, and that can certainly make the snow surface very cold. Frequently, though, when we get that really cold Arctic air mass, we also have clear skies, and those suck even more heat out of the snowpack and make it even colder. Now, here's the thing. In many parts of the world, Utah is a great example. Fall can be just a beautiful time with dry weather and fairly warm weather. We don't have that bitter cold weather, but the depth hoar forms regardless, and that's because you have just a few moments of sunshine each day on those slopes, but you have hours and hours and hours all night long and most of the day when that snow is exposed to a very clear, cold sky that allows that snow, despite the warm air temperatures, allows that snow to get much, much colder than the air. And in Utah, in that winter, in the fall of 2019, moving towards January 2020, this was the situation we had. We had early snow on shady slopes. It formed depth hoar because of those clear skies. And then on south-facing slopes, as you can see here, it was bare ground. So by the time the snow really kicked in, there were no persistent weak layers. And we can see that here in this chart from the Alta ski area of total snow depth. At the beginning of the season, we had about 20 inches of snow on the ground that was exposed to those clear, cold nights. They made the snow surface cold while the snow at the ground stayed warm, and we formed depth hoar. That particular winter, we had a huge storm that quadrupled the snowpack in kind of mid to late November, and we had an early avalanche cycle on that faceted depth hoar at the ground. Then again, another big storm kind of mid-December that caused another avalanche cycle, but then it began to bury that depth hoar fairly deeply, about 6 feet of snow on top of it, which allowed it to start to heal. So when we talk about depth hoar, it typically does take some amount of time. You usually see it coming every winter. It takes 7+ days to form, forms right at or very near the ground with that thin snow. And then it's, air temperatures certainly play a role, but it's those clear skies that really make the snowpack very cold. And in a lot of places, it's more common on north-facing slopes, but as you go up in higher latitudes where the sun angle is so low, that snow can be draped over all aspects and depth hoar can be found around the compass. Now, all of a sudden, that had healed, and what we began facing that January 2020, we were tipped off by the DOT when they mentioned that avalanche, was in the blink of an eye, some small facets had formed from a process called radiation recrystallization that created these facets on south aspects. They form in the blink of an eye, and they can look just like this. This is a great photo taken by the Yellowstone Club Ski Patrol. It takes a really unique balance of long wave and short wave radiation, and because of that, it forms on a south-facing slope, and here's how they form. This is a southwest facing aspect, and there's a really cool process going on right here, and that is the sun is penetrating the snowpack, and it's warming up the snow just an inch deep, not even, and it's creating this little thin crust. What's important though is that the snow right on top of it hasn't melted or gotten wet. The reason why is that the sunshine is able to penetrate the snow and warm up the snow underneath. So it warms it up and it creates this little crust. This crust forms when the warm melted snow refreezes. But the snow right on the surface, this stuff right here, stays cold because it loses heat to the clear sky. What that does is sets up a strong temperature gradient in the top, maybe just centimeter of snow. And when we look under magnifying lens at the snow on the surface, we can see that it's starting to facet. We'll be monitoring this and seeing what happens. We're going to start getting some snow this weekend, not a lot, but it could be enough to preserve this weak layer. So we'll have a little thin layer of facets on top of a very thin little crust. Unless we get a lot of wind or much warmer temperatures, and then it could melt this layer or blow this layer away. So to summarize, what it takes is a precise balance of shortwave radiation coming in to warm the snow just under the surface, long wave radiation going out to cool the very top layer of snow, and then we end up with cold snow over very warm snow. That creates a big temperature gradient because it's a decent temperature difference, but it's over such a short distance. And it really requires that precise balance. So it doesn't happen all the time, but when you get that precise balance, it can happen in the blink of an eye. That's what we saw that winter. We went through the early snow and the early avalanche cycles, and then the crux was, and what I missed and my team struggled to get on top of, was there was a brief period of dry weather when we had that precise radiation balance. It also, the challenge for us was it happened over the holidays. Christmas, New Year's, all that stuff was happening, and it was hard to keep track of things. We got a storm right around the 1st, followed by another one in the first week of January, and that's what caused that avalanche cycle on those south-facing slopes, that avalanche situation to completely reverse itself. Hi, this is Mark with the Utah Avalanche Center. I'm in Dry Fork, just behind Alta. This is a snowmobile-triggered avalanche that happened yesterday. A couple things stand out. One is that it was on a southwest-facing slope. Generally, we have a strong snowpack on south aspects, and we do down deep. It's very strong, but What we have right now is a crust right in here with a thin layer of weak snow right next to it. This is going to be an issue at least for a little bit. Stay tuned. For right now, it's going to cause avalanches. So, for these facets from this radiation recrystallization process to occur, it can happen in just a matter of hours, like the blink of an eye. It's in the top about 10 centimeters of snow, although it's typically within the top few centimeters. And it's that balance of long wave out, short wave in, and because it requires sunshine, it is on sunny slopes. Now, a similar process is called diurnal recrystallization. It's very similar, but it occurs from just the normal warming during the day and the cooling at night. So it doesn't require that exact balance. It can happen quite frequently throughout the winter. And here's how it plays out. We have all these components of energy. Heat comes in and out of the snowpack. During the day, we have our snowpack, and the upper layers of snow warm up from all these energy sources. So you have warm snow above relatively cold snow because the snowpack is still fairly cold down underneath. But then at night, it flip-flops, and we have very cold snow at the snow surface. Just like with depth hoar, it's from those clear skies that allow the snowpack to dump heat through that long wave radiation loss. And then compared to that very cold snow on top, the snow down a little bit deeper is actually relatively warm. So now we have cold snow over warm snow. It's a little more complicated than this. And so the way it plays out is you have your snowpack, it warms up during the day, so you have warm snow over cold snow. And then at night, when it initially begins to cool off, because snow insulates fairly well and doesn't move heat through conduction too fast, you end up with very cold snow over some warm snow, over some cold snow. As the night progresses and the snow surface cools off even more, you have very cold snow over relatively warmer snow. And then by the next morning, things begin to heat up again. You have some warm snow over cold snow over slightly warmer snow. Now, bottom line, and for me, the way I think of it is, it's these clear nights that are just so important. They pull so much heat out of the snowpack and cool the snow surface down way, way below what the air temperature is. And it was so important, in fact, that when I worked in Utah, one of the forecasters there, Trent Meisenheimer, would always send me a text when we went into one of these periods of high pressure. He'd send me a text saying, clear night number 1, and the following night, clear night number 2. And it was our way of keeping track of these events because he really honed in on the most important factor was those clear skies at night, pulling so much heat out of the snowpack and cooling it off so much that it would set up those strong temperature gradients between day and night. And you usually see this coming with this process. It starts forming in just a matter of hours, but typically these periods of high pressure with warm sunny days, clear cold nights, happens over a number of days. It's within the top 10 centimeters, although it's usually the top few centimeters. And it's that long wave loss at night really cools the snow, and then a little bit of warm air, a little bit of short wave in during the day warms it up. Mostly on shady aspects, but depending on the time of year, it can form other places too. Now, the last type of near surface facets comes from melt layer recrystallization. It requires a layer of wet snow or a melt layer. Often that's from rain, which it seems like we're seeing with a little bit increased frequency these days, but it can also just be from warm air temperatures or solar radiation that causes the snow to melt a little bit, so you have that wet layer of snow. And then what it takes is a little bit of new snow falling on top of it. So what you end up with is cold, dry snow on top of warm, wet snow. Because it's wet, we know that it's 0 degrees Celsius. And as long as it's still wet and hasn't refrozen yet, you end up with cold snow over very warm snow. That cold snow gets even colder as you move into night if the sky's clear and it loses its heat. And then you have very, very cold snow over warm snow. And that process will continue as long as you have that wet layer. Once it freezes, the process slows down, but it can continue a little bit longer because of the temperature gradient around that ice crust. So It can happen in just a matter of hours. It can continue a little bit longer as that crust starts to get buried. Initially in the first few centimeters of the snowpack, going down to about a meter deep. Mostly it's from that long wave loss out that really cools that layer of dry snow on top. Some short wave in can contribute if that's what creates that wet layer. And then because rain, if that's the primary mechanism, falls on all aspects, it forms around the compass. Lastly, we want to talk about surface hoar. The difference between all these other things in surface hoar is that those other weak layers form when snow crystals change shape. Surface hoar, the crystals form directly in that shape, just like frost forms directly onto your windshield. When that frost forms on the snow surface, we get surface hoar. You've probably all seen what it looks like, these sparkling feathers or flakes of snow on the snow surface. The process is just like what I observed this one morning. So you have this warm water vapor in the air. Adjacent to you have these trees, which are much, much, much colder, just like your car windshield. When the warm water vapor contacts those very cold trees, it instantly freezes and you get frost on the trees. Now the question is, why is the snow surface colder than the air? And the answer, if you've noticed a theme in this video, is it's that long wave loss, mostly during night. Just like frost on your windshield, it can form in just a matter of hours. It forms right on the surface. The primary thing is that long wave loss. Typically forms on all aspects, but it can definitely be more prominent on shady aspects. And then I think the really interesting thing about surface hoar is that it's not just the aspect. It can form on one slope versus another. Maybe one slope has intermittent tree cover, which helps shade the snow just a little bit from those clear skies at night. And you'll see some surface hoar, but not as much. As you go to a slope that's really exposed to that clear sky, where that snow surface got much colder, you'll see bigger, thicker, taller maybe crystals of surface hoar. And then whether or not it gets buried and becomes a problem is why surface hoar is so spooky. Some wind can blow through and knock it down and destroy it on some slopes while leaving it on others. And it can be very pockety in how it survives. So we've covered these 5 different processes and the resulting crystals: depth hoar, radiation recrystallization that forms facets, diurnal recrystallization, melt layer recrystallization, and then surface hoar. And then, except for depth hoar, the really tricky part, this is why we get out in the field on a regular basis, is that these facets can form sometimes in just a matter of hours, in the blink of an eye, and you have to be on it. The second thing that stands out, hopefully you've noticed by now, is that the common theme that really drives so many of these processes is the ability of snow to lose so much heat through the long wave radiation exchange with a clear, cold sky. So this video is just a start on your journey to fully understand all of these weak layers and the processes that involve all these forms of energy, heat coming in and out of the snowpack, and what leads them to form, why they form in some places and not others. Ultimately, learning to understand these patterns should lead to a better understanding of patterns of avalanche activity, and hopefully you'll better be able to forecast big changes that we struggled with in January 2020 when there had been avalanche activity on north-facing slopes, and fairly suddenly it shifted and avalanche activity started happening on south-facing slopes. Once you do, it'll unlock a whole new world. It's a lot to keep track of. Some things are easy to see, like where there's sun and there's shade on a slope. Other things are a little harder to see, and mainly that's how long wave radiation comes in and out of the snowpack. That can be some clouds that move in that shade the snow from the cold sky. That can be a little bit of a intermittent tree cover. It could be some other terrain features. And I hope you can appreciate how that long wave radiation exchange is really, really important to the formation and then patterns of these avalanche activity. Good luck on your journey. Stay tuned for Bruce's next video in part 3.